In the second part of the lecture, we will study an algorithm for linear time suffix array construction using induced sorting. But first, let's recap what are suffix arrays. Suppose we are giving a suffix tree. In a suffix tree, each path from the root to a leaf corresponds to a suffix in the text, and the leaves are marked with the number of positions at which this suffix starts in the text. So now we sort the suffixes lexicographically and record the sequence of the corresponding position indices. And what we get by this procedure is called a suffix array. Let's consider a simple implementation of suffix array construction. Here we first define a function that returns a function that in turn returns a suffix starting at the position I if it is passed an argument of the position I. You can do this in Python because in Python functions are treated as first-class citizens. So you can define a function that will return a function. And we need to do this to use this function as a key for sorting. So in the main construction function, we first simply initialize the suffix array with a list of all indices from 0 to the length of the text minus 1. And then we resort this list using as a key that corresponds to the suffixes. This is also possible because in Python you can pass any key to the sort method. In this case, we use suffixes as a key, and if we sort suffixes, they're going to be sorted lexicographically, and the corresponding position indices will be sorted respectively. So this is a very naive implementation of suffix array construction that makes use of these specific Python methods and functions. The runtime of this implementation depends on the implementation of the particular sort method, and it usually is going to be big O of n cubed or big O of n squared times log n. In this part of the lecture, we will consider a more complex implementation that will allow to construct a suffix array in linear time, that is big O of n. This is very important if you have long texts and the difference between n cubed and n becomes really important. The technique that we will be using to construct suffix arrays in linear time is called induced sorting. The idea of induced sorting is that we can sort only a fraction of all suffixes of a text, and this will be enough to order the other suffixes correctly. We will use additional data structures to ensure this behavior. The algorithm that I will be presenting next is described in full detail in the textbook of Olga called Bioinformatics Algorithms. You can look it up there with all lemmas and all proofs that are needed. First, let's introduce some definitions. Consider a string S of length n with a sentinel. Then for every position of the text except the sentinel position, we can classify them in being L positions or S positions. A position P is called an L position, where L means larger, if the suffix starting at position P is larger than the suffix starting at the next position. Analogously, P is called an S position for smaller if the suffix starting at P is smaller than the suffix starting at the next position. The last position of the text, the sentinel, is always defined as an S position. This definition implies that no two suffixes of the text are identical, which is indeed true for any text. So here we have an example. Here we have just the index of the position in the text, then we have the text, and here we introduce an array type which stores information about whether the corresponding position is an L position or an S position. The array type can be computed in linear time if we scan the text from right to left And the information can be stored as a bit vector, for example, where 1 represents S and 0 represents L. We're not going to use this representation. We are going to just write S or L, but you have to keep in mind that this can be implemented as a bit vector. So how can we construct the array type? For the last position of the array, by definition, we just define that it is an S position. And then for every previous position in the array, we can compare the character at the position P with the character at the next position. And if it is larger, then we can directly define the position P as an L position. If it is smaller, then we can directly define it as an S position. Otherwise, if the characters at position P and position P plus 1 are identical, then we just set the type of position P as equal to the type of the next position. And you can make sure that in this case, the array type will be defined correctly. Now, an S position that is located to the right of an L position is called an LMS position for the leftmost S position. And a pair of positions I and j is called an LMS interval of the text if either I is smaller than j and both I and j are LMS positions as defined above. And there is no other LMS position between I and j. Or I is equal to j and they are both equal to the last position of the text. And obviously, each LMS interval is associated with an LMS substring between positions I and j, including the ends. Now, by this definition, the last position of the string is always an LMS position. And whether a particular S position is also an LMS position, so the leftmost S position, can be determined in constant type using the bit vector type by just looking up the type of the position to the left of the particular position. Here again, for the same example, we constructed a few more data structures. First, we have an array here which marks all the LMS positions in the text, and then we have all the LMS substrings of the text. Now with these additional data structures, we can proceed to our induced sorting algorithm. A bird-flight view of the algorithm is as following. We have an input sequence S and an array pose, which is the output suffix array of S. So what do we do? First, we scan S to compute type array, which we can do in linear time as we have just saw. Then we scan type array to find all LMS positions and all LMS intervals and all LMS substrings in S, which also can be done in linear time. And then the actual algorithm has two phases. First, we sort suffixes corresponding to all LMS positions. In the second phase, we sort all remaining suffixes of S. And then we just output the suffix array. The first phase is more difficult to understand than the second, so we will start with considering phase 2. We also start with phase 2 because phase 1 uses elements of phase 2. First thing that we do, we split the resulting suffix array into buckets. A bucket is a maximal interval of suffix array pose in which the reference suffixes start with the same character. If the list of suffixes is lexicographically sorted, by definition, all the suffixes that start with the same character will come one after another in this list. So we can do this. The number of buckets, if all characters of the alphabet appear in the text, is going to be equal to the number of characters in the alphabet plus 1 for the sentinel character. Without losing the generality, we now can assume that that's the number of buckets for our text. We can prove a lemma that in a single bucket of the suffix array, all L positions appear before S positions. As an idea of the proof, let's consider a simplified alphabet that consists only of 3 characters, A, B, and C, and A is smaller than B, and B is smaller than C. And consider the bucket starting with B, bucket for all suffixes starting with B, and an L position Q and an S position P in it. By definition of L and S positions, the suffix corresponding to Q is going to be of the form of some B, so a number of character B, and then a character A, because otherwise it wouldn't be an L position. And position P, suffix corresponding to position P, is going to be in the form of some B characters and then a C character. So it doesn't matter how many B characters we have, suffix of this form is going to be always smaller than suffix of this form, and so the L positions should come before S positions. So every bucket can be split in 2 parts. First one corresponds to all L positions, and the second corresponds to all S positions, and they are going to be always sorted first L positions and then S position. If you are attentive, you would know that for the sentinel character bucket, there's going to be no such split because the suffix corresponding to the sentinel character is always an S position. Now, how can we sort all non-LMS positions? An interesting insight is that we can use sorted LMS positions, which are a subset of S positions, to sort all the L positions correctly, and then we can use the sorted L positions to sort all the S positions. And this is why the algorithm is also called induced sorting, because a subset of suffixes allows you to sort correctly, to place correctly another subset of suffixes. So some suffixes induce ordering of the others. So how do we proceed with the algorithm? First, we initialize the suffix array pose with a known at each position. And then we mark beginning and end of each bucket. Then we write all the sorted LMS positions to their respective buckets. This is done, the sorting of LMS positions is done in phase 1, so now we take for granted that LMS positions are correctly sorted. Here is an example. The familiar sequence S, the type array, and the LMS positions are marked with stars. So in the preparatory phase, we just put all the LMS positions in the corresponding buckets in the right order. Now, in the actual production step of the algorithm, we scan the suffix array from left to right, that is from start to the end with an index R, and each time we look at the position that is stored at this index. If nothing is stored, pose of R is unknown, then we simply skip this index. Otherwise, we look at the position in the text that precedes the position that is stored at this index. And if this position is an L position, we will put this index, this position, at the first non-occupied position in the corresponding bucket. If the position preceding pose of R is an S position, we again skip this index. And as a result of this procedure, of this one single scan, all L positions will be entered in the suffix array in the correct order. Now let's look at the example. So that was our prepared array, and we start at the position 0 of it, where the sentinel character is stored. So what we are doing, we are looking at position that precedes the sentinel character in the text. So it is an L position. So we can put it into the right place in the suffix array because it starts with an A. We just put it at the first unoccupied position of the bucket corresponding to A. And we move one position down the text. Now we are looking at a position that precedes position 20 in the text is going to be T. It is also an L position. So what we do, we put it into the first unoccupied position of the bucket corresponding to T. Then we move down one position, one index in the suffix array. This is unoccupied, so we skip it. We move down again, and now we are looking at position preceding position 5, that is position 4. It is again an L position, so we put it into the right place in the bucket, so in the next unoccupied position, and so on. So this is what we're going to get after we complete the scan of the suffix array. Now, to sort the S position, we do almost the same thing, but now we iterate through the suffix array in the other direction, from right to left, that is from end to the beginning. The rest is very similar. If at the index R in the suffix array an unknown is stored, then we skip this index. Otherwise, we look at the position that is preceding the position stored at index R. If this position is an S position, we enter it at the rearmost non-occupied position in its bucket, so at the starting from the end of its bucket. And then if it is an L position, then we just skip this syntax. We continue with the example. So that's what we got after we put all the L positions in place. Now we start from the end, and first of all, we can remove all the LMS positions that were put in phase 1, because we will just enter them as normal S positions. We look at the last position of the suffix array. Here, 9 is stored. So we're looking at position 8. It is an S position, and we put it into its right bucket at the end of the bucket. Then we look at the position 12, and preceding position is position 11. It is also an S position, so we put it into its bucket again, and so on. And at the end of the procedure, we put all the S positions in place. So to summarize phase 2, what we do, first we enter sorted LMS positions into pose, and then we sort all the L positions, all the L suffixes based on sorted LMS suffixes, and then we sort all S suffixes based on sorted L suffixes. The runtime analysis here is pretty straightforward. In step 1, initializing the array and setting the bucket pointer can be obviously done in linear time. And steps 2 and 3 all entail only one scan through the suffix array. So this can be done in linear time. And thus, induce sorting from sorted LMS positions, so the phase 2 of induced sorting, can be done in linear time. The question is, how can we prove that these steps ensure that all positions in the suffix array are entered in the correct order? We can prove a lemma for correctness of this placing. Assuming correctly ordered LMS positions in each bucket in the suffix array, we can show that after step 2, all L positions in the text can be found in the suffix array at their correct places. The idea of the proof is the following. Let P be a text position with rank R in the suffix array, and position preceding P is an L position. Then P minus 1 has a rank R prime, which is larger than R by definition of an L position, because the suffix at the position P minus 1 have to be larger than the suffix at position P. So we will need to put this position in the suffix array later than P. Another thing is that each L position is to the left of either L position or an LMS position, so every L position P minus 1 will be induced either by an LMS or an L position P. And this is why we start with sorting the L positions. One can inductively prove that all L positions are correctly placed if we follow this procedure. Analogously, we can prove the correct sorting of S positions. Assuming correctly ordered L position in each bucket of the suffix array, after step 3, all positions in the text will be found in their correct places. The idea of the proof is very similar. Now let P be a text position at rank R in the suffix array, and P minus 1 will be an S position. Then the rank of P minus 1 will be smaller than R by definition of an S position. Then, obviously, every S position will be found to the left of either L or S position. And this is why we can discard the sorting of LMS positions, so we can remove the LMS positions from the suffix array before starting sorting S positions. And again, one can inductively prove the correctness of each individual step. You can look up these proofs in the textbook Bioinformatics Algorithms. Now we need to go back and describe phase 1. Phase 1 proceeds as following. First, we enter unsorted LMS suffixes into the suffix array. Then we sort all L suffixes based on these unsorted suffixes. Then we sort all S suffixes based on sorted L suffixes. Then we will create several auxiliary data structures, arrays of different length, that will allow us to reconstruct the correct sorting of LMS suffixes in case when all LMS substrings are unique. If the LMS substrings are not unique, we will need to do additional work on these auxiliary data structures to recursively sort the new suffix array post prime. And in the end, we're going to obtain correct ascending lexicographic order of the LMS suffixes. I will describe now all these steps in the detail. One thing that one needs to note here is that the first 3 steps are the same as in phase 1, but the LMS suffixes are not sorted yet. I will show that you can sort LMS substrings using this procedure. Now, to go in more detail, in the first step of phase 1, first we create and fill the type array that we can do in linear time. Then we create a new array P of the length that is equal to the number of LMS positions. Then we can scan the array type from left to right and put each LMS position into its correct bucket. And simultaneously, we put each LMS position into the P array starting from the beginning. So in the array P, we just store LMS positions, and in the suffix array, the LMS positions are sorted into the correct buckets, which means that their substrings of the LMS suffixes of length 1, corresponding to the first position of the suffix, are at least sorted correctly. Now, in step 2, we scan the suffix array from left to right, just in phase 2. And if the suffix starting at position to the left of the stored position is an L-type suffix, we put it to the current beginning of the corresponding bucket, just as we did in phase 2. In step 3, we scan the suffix array from right to left in the backwards direction, and if the suffix starting at position to the left of the stored position at the index I is an S suffix, then we put it to the current end of the corresponding bucket, exactly as we did in phase 2. And one can show that after this procedure, all the LMS substrings are sorted correctly. Now, an LMS substring is just a substring between 2 LMS positions, whereas an LMS suffix is a suffix starting at an LMS position that is a substring from this position to the end of the string. So, correct sorting of LMS substrings doesn't ensure correct sorting of the suffixes, because if 2 LMS substrings are identical, their correct ordering will be defined by the part that is beyond the LMS substring. Therefore, we need to proceed and solve these collisions. The idea here is to rename LMS substrings and sort them again. What we need to find is which LMS substrings are identical. But as I said, the first 3 steps ensure that the same LMS substrings appear next to each other in the suffix array. So what we do to solve this problem, we create an empty array ln of the same length as the whole string s, where ln stands for lexicographic naming, and store new names for the LMS substrings in this array. So what we do for each LMS position, we compare the LMS substring to its previous substring, and if they are different, we introduce a new symbol to represent it. Otherwise, we use the same symbol and store it in the array ln. Now we have renamed all LMS positions based on the ordering of the corresponding LMS substrings, and positions that correspond to the identical substrings got the same name. Now we collect these new names in a string called s prime here. If all the names are different, then the number of these names is equal to the number of LMS position, and in this case we can directly compute a suffix array pos prime for the string s prime, and this will give us the correct ordering of the LMS positions. But if some LMS substrings are identical, then this will not be possible. So we need to do an additional step. What we do here, we just obtain the same procedure to the suffixes defined by the string s prime. We can compute the suffix array directly for this string, and this, after recursion, give us the correct ordering of the LMS positions in pos prime. And now we can define the ascending lexicographic order of all suffixes starting at LMS positions. Now let's see if I can make it more clear using an example. So consider a sequence S like this. Here P is just position in the sequence, and this is the computed type array, and all the LMS positions are marked with a star. Now, as I said, the first 3 steps of phase 1 ensure that all the LMS substrings are sorted correctly lexicographically. So when we construct the lexicographic naming array, the corresponding symbols can be entered like this. Here I use numbers to represent every LMS substring, but of course you can use any character, any set of characters that can be lexicographically ordered. So here the numbers represent nothing but lexicographic order of the LMS substrings. And here you see that the substrings at position 8 and 11 are problematic because they are identical, ATTA, ATTA, so the difference between these LMS suffixes is beyond the corresponding LMS substrings. Now we just compress these characters in the text S prime, and here P prime is just an index in the text S prime, and S prime we call the reduced text. And P at the position of the index will just represent the original positions of the LMS positions in the text. Now what we can compute is a suffix array pos prime of the reduced text S prime, which is here. And here, since we were able to order all the suffixes of the reduced text S prime correctly, in the post prime of R, we have the reduced what we can do now, we can compute the suffix array for the reduced text as prime using just exactly the same idea. Here we are lucky, and you can work it out for yourself, that all LMS substrings of text as prime are different. So when we compute the suffix array of the reduced text, we end up with all different LMS substrings, and thus we can order the suffixes correctly and without any conflicts. So here this is called iteration step, and we need to do only one iteration to compute the suffix array of the reduced text that will give us the correct ordering of all the LMS suffixes corresponding to the LMS positions. But this recursion can be necessary several times. So how can we know that the recursion step doesn't blow up our runtime? There are a few observations that we can make. First, the alphabet size in the reduced text can grow initially, just as we saw. Instead of 4 letters in the example here, we have 6 different characters. But it is bounded by the number of positions in the text. And after each step, after each recursion step, the length of the reduced text decreases because there is only a limited number of possible LMS positions in the text, for obvious reasons. First, the first position is not an LMS position because there is nothing to the left of the first position, and there must be at least one position between 2 consecutive LMS positions. Otherwise, the second one is not going to be the leftmost, right? So this allows us to compute the total runtime for this induced sorting construction of suffix array. To determine LMS substrings and to conduct the whole alphabet replacement step will take linear time for obvious reasons, because we only need to do a limited number of sequential scans of the text. Then to sort LMS substring recursively, we just need to apply the same estimate that we make for the text that is only half of the length of the original text. So we will see how these recursive steps will sum up. And then sorting of non-LMS suffixes, as we have seen in the previous part, is also takes on the linear time. So let's compute the runtime recursively. So let's compute the runtime by induction. For the text of length 1, obviously the runtime is big O of 1. And then let's compute the runtime for the text of length m. So we have this linear part here. Then we have the same function, the same estimate for the text of the half of the length. And then we have another linear part. So we sum up this linear part to this constant by n term. And then we need to compute this. But by induction, we can write it as the same constant times n by 2 plus the estimate for the text of the quarter of the length. And then we can continue this, and we can show that this is bounded by Cn times this sum. And luckily, this series sums to 2. So we can show that this whole runtime is bounded by 2cn plus a constant term, which will be linear in n. So we can show that the runtime of the whole algorithm is linear in n, which was our goal. Now let's summarize today's lecture. In the first part, we have considered the Ukunin's algorithm for linear time construction of suffix trees. During that, we have introduced the concept of suffix links, which are useful also in other contexts beyond the suffix tree construction. In the second part of the lecture, we considered a linear time algorithm for construction of suffix arrays that uses induced sorting. And we have observed the following behavior. First, we can use sorted LMS suffixes to induce sorting of L suffixes. Second, we can use sorted L suffixes to induce sorting of S suffixes. And we can use the same induced sorting procedure recursively to sort the LMS suffixes in the first place. Thanks a lot and see you on Tuesday.